Heat transfer analysis of microchannel using fluids. Abstract. In recent time, due to high performance of electronic component, the heat generation is increasing drastically. Due to this scenario, heat dissipation becomes a major issue in efficiency, promation and stable operation. Silicon-based microchannel heatsink fabricated using semiconductor production technique plays important role in cooling devices. The effect of the thermophysical properties of working fluids on the performance of microchannel is tested, or we can say investigated. For this purpose, the different working fluids are selected: water, hepthane, ammonia, methanol, and ethanol. Keywords: heat transfer, microchannel, different coolants, natural convection, heat transfer, heat sink, cooling, micro heat sinks. Introduction. Nowadays the electronic devices become compact. Due to compactness of this devices, there is huge heat generation in this devices. Hence, for the safety purpose, heat should be removed from this devices continuously. So the purpose of cooling system is to maintain the temperature in certain limits, such as 1. Natural cooled heat sink. 2. Forced cooled heat sink. 3. Superconducting radiators. All these conventional cooling systems are useful when heat dissipation rate is below 100 W/cm superscript 2, but when this rate becomes more than 100 W/cm superscript 2, then these conventional cooling system fails to cool the devices. For cooling purpose of this devices, microchannel heatsink are used. Microchannel heatsink was first introduced by Tuckerman and Pease in 1981. Later on, lots of research work has been carried out on microchannel, especially to increase S's performance of microchannel heatsink. Microchannel has high heat transfer coefficient and less thermal resistance. This is the main advantage of the microchannel heatsink. Microchannel heatsinks are widely regarded as being among the most effective heat removal techniques for space-constrained electronic devices. 2. Literature review. Ali M. A. Solomon et al. State that in the study, an experimental investigation to the performance of the solar cells coupled with heatsink is presented. Indoor experimental setup was designed and assembled to investigate the impact of using heatsink cooling system on the performance of solar cells. Halogen lamps used to simulate the solar radiation, and the study is carried out at different solar radiation values. Moreover, the study is carried out at natural and forced air to cool the heatsink. The results show that using heatsink cooling system enhances the performance of the solar cell. Temperature of solar cell decreased by about 5.4% and 11% by using heatsink cooling system at natural and forced air over the heatsink, respectively. Moreover, the efficiency and power of the solar cell system increase by about 16% when heatsink cooling system is used. 1. Mushtaqi Hassan et al. State that in this paper, using of the phase change materials, PCMs, in a microchannel heatsink, MCHS, is numerically investigated. The air is first used in heatsink, and then 4 phase change materials, paraffin wax, Nicosane, P116 and RT41, have been used as cooling mediums in different types and different configurations at different ambient temperatures. Constant heat flux is applied on the base of heatsink, and mixed convection and radiation boundary condition is applied at the top surfaces of heatsink. The results showed that using of the phase change materials in microchannels heatsink with different configurations lead to enhance the cooling performance of micro heatsink. The phase change material should be selected according to its melting temperature according to the certain application, as different phase change marshals caused different values of reduction in heatsink temperature in range of ambient temperature due to difference in melting temperatures of PCMs. The cost of materials depends on the classification of the PCM, organic and inorganic, and quantity of PCMs used in a certain application too. Afzal Hussain, Kwang-Yang Kim et al. State that the present study deals with the numerical optimization of microchannel heatsink with the help of surrogate analysis and evolutionary algorithm. 2 design variables related to the microchannel depth, width, and end width are chosen, and their ranges are decided through preliminary calculations of 3-dimensional Navier-Stokes and energy equations. Objective functions related to the heat transfer and pressure drop I.E. thermal resistance and pumping power are formulated to analyze the performance of the heat sink. Water with temperature-dependent thermal properties is used as coolant for steady laminar fully developed AO in the silicon microchannels. Using the numerically evaluated objective function, polynomial response surface is constructed for each objective function. Evolutionary algorithm for multi-objective optimization is performed to obtain global Pareto optimal solutions. Trade-off between objectives is found and analyzed with the design variables and .AO constraints 3. Sunil Kumar et al. State that the nanofluids have increased interest in many engineering fields due to its excellent thermophysical properties, which can be easily used in microchannel heat sinks by many roles for performance improvement. The purpose of this review summarizes the important published articles on the enhancement of the convective heat transfer in microchannel heat sinks using nanofluids. Numerous studies have been done to find the effect of different nanofluids flow through microchannel heat sinks on thermal performance. In this work, a comparative study is also carried out to select B microchannel heat sink shapes for maximum heat transfer and minimum friction losses for 3. Working procedure. Fig. Schematic view of the experimental facility: 1 mini pump, 2 inlet pressure gauge, 3 inlet thermocouple, 4,5,6 test module, 7 outlet thermocouple, 8 outlet pressure gauge, 9 fan system. It consists of following devices: mini pump, inlet pressure gauge, inlet thermocouple, test module, outlet thermocouple, outlet pressure gauge and the fan system. First we have to turn on the heater. After turning on the heater we have to set a measurement of current and voltage by using the multimeter. The working fluids which are stored in reservoir are allowed to pass through a microchannel one by one. Then the reading are taken through a test module. 4 properties of working fluids. 1. Water. Warm water vibrates longer than cold water. The thermal conductivity of water is high and rises to a maximum at about 130 degrees Celsius. Water has unusually high viscosity. 2. Ethanol. Ethanol is colorless liquid with the pleasant smell. It is completely miscible with water and organic solvents and is very hygroscopic. 3. Methanol. Methanol appears as a colorless, fairly volatile liquid with a faintly sweet pungent odor like that of ethyl alcohol. Completely mixes with water. The vapors are slightly heavier than air and may travel some distance to a source of ignition and flashback. 4. Ammonia. Ammonia is a colorless gas with a characteristically pungent smell. It is lighter than air, its density being 0.589 times that of air. Result and discussion. The heat transfer capacity as the function of the operating temperature and the test module is filled with the different working fluids. And they observed the heat transfer capacity of these different working fluids. We also observed that except the water, other 4 working fluids shows that, when the operating temperature increases in the heat transfer capacity also increased. And in case of water, as the operating temperature increases the heat transfer capacity is rapidly increases. So we can say that the water can gives the best result than the other working fluids. The following graph can shows the operating temperature varies with the heat transfer capacity. 6. Conclusion. Microchannels are capable of removing heat up to 1000 W/cm2 due to their high thermal conductivity. It is clearly seen that for operating temperatures below 50 degrees Celsius, it is more advantageous to use ammonia as the working fluid to maximize the heat transport capacity. When we used water as fluid, we can conclude that as the temperature increased, the heat transfer capacity of water is increased. Water is preferable if the operating temperature is higher than 50 degrees Celsius. According to that, we can say water can gives good or better result than any other working fluids.